So I usually find it quite confusing. We're kind of cheating here, so we're guessing what the Fourier transform of the unit pulse train is, and then we're trying to prove that our guess is correct. So this is our guess. So here, this is a guess to be the Fourier transform of the unit pulse. So if this is the Fourier transform, we can take the inverse discrete time Fourier transform. So this is what we're doing here. We're taking the inverse discrete Fourier transform. So this goes here, and this is the formula for the inverse discrete Fourier transform, but this is equal to this, so we put this here and becomes this thing here, and when we solve this integral we have this result here. So this is the inverse discrete time Fourier transform. So this is our unit impulse train, and now we need to prove that this is indeed a unit impulse train. So what we do is that we see that this is geometric sum. We use this other mathematic trick to find a closed form for this geometric sum. Here we are replacing c, so c to the power of k. So c in this case is equal to e to the power of j 2 pi capital N times n. So we have that for k equals to, going from the summation from k equals to 0 to n minus 1, and we can simply go from 1 to capital N, and then we have this c multiplying here. Now with this we have that goes from here to here, so we put that this s in evidence. So s is times c minus 1 is equal to c to the power of n minus 1, and then we get that this is the s is equals to c to the power of capital N minus 1 divided by c minus 1. So we use this trick here, and then we replace c by e to the power of j 2 pi divided by capital N times n, and we find this closed form. And now we need to prove that this is a unit pulse train. So this sum must become n for n equals to m times n. So what we do, we replace here n equals to m times capital N, and then we see that this part here is an undefined case, so we have a 0 divided by 0, but on this part here we have that the this here is equal to 1, and then this sum becomes n as desired, and for n different to m times capital N, it needs to be 0, and we can look here. So when we plug this here, and we see that the numerator is unequal to 0, the denominator is unequal to 0, but the numerator becomes 0, and then the sum is indeed 0. Yeah? So we proved that our assumption was right, and we have this equation here for the unit pulse train. So now we can use this expression for the unit pulse train in the time domain, and we can compute the Fourier transform. So we have this here, so we had our signal, and we're multiplying it with the unit pulse train. So the unit pulse train is given by this formula. So we have here that this downsampled version of an already sampled signal. It's like this. Then if we take the discrete time Fourier transform, and then it results in this equation here. So what we're doing is we're taking the dtf, so the discrete time Fourier transform. So this is here, and then there is a summation from minus infinity to infinity, and here we have the e to minus j omega n. So from here we can get this equation here, and this is the result. So we have that the discrete time Fourier transform becomes 1 divided by capital N, and this summation going from k equals to 0 to n minus 1, and then we have this x of minus 2 pi divided by n times k plus omega. So this shows that the sampling still included the zeros leads in the frequency domain to multiple shifted versions of the signal spectrum. So we can also call this multiple shifted version of signal spectrum as aliasing components. So this is a graphical visualization of what indicates here. We have the signal spectrum, and we have the original spectrum, and we have aliasing components. So there are multiple shifted versions of the original signal spectrum. So these aliasing components periodify the spectrum according to this new sampling rate, which is 1 divided of capital N, or 1/nth of the old sampling rate. Hence the new period is 1 divided by n, the old period of 2 pi. So let's observe that the spectral components don't overlap if their bandwidths are below 2 times pi divided by capital N for complex signals, or for real signals it should be below pi divided by n. So this is a very important that the spectral components don't overlap, because if we want to reconstruct the original signal, hence we need to make sure that the aliasing components don't overlap by suitable filtering at the high sampling rate to prepare for the downsampling. Yeah? Let's observe also that the term aliasing in literature is sometimes only used for overlapping aliasing components, but like we do here, we use it more broadly, that we just mean that any additional shifted frequency component, we also call it aliasing. Yeah?